Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hi, this is Mr. T with a tutorial on counting principles. This is the second in a three-part series on probability and statistics. We will be talking about something called permutations, which is when we are arranging things, and combinations when we are making or selecting groupings. We talked a little bit about counting principles in the probability video. We talked about the counting multiplication property or principle, and we'll be building that on that today. Some of the formulas that we use for probability use a new operator that may be new to you called the factorial operator. It's the exclamation point. It's a math operator, and the way it works is the number, it follows the number, and to evaluate that you take the number and multiply it times all the numbers starting there down to 1, and you would multiply that string of numbers together. So for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. Let me bring a graphing calculator on here to show you how to do it on the calculator. Now it may get tedious if we had a big number to do a factorial, so let's look at maybe 11 factorial. So type in the 11, and the stuff we're going to be using today is in the math menu and under probability. So I'm going to go over to probability, and the fourth item there is the factorial operator, the exclamation point. And now we just press enter, and you can see that factorial numbers build up quite quickly here. So this is a big number when we did the 11 factorial. So we're going to be talking about permutations first. They are arrangements, and we are selecting from a group of items, a pool of items, of n items, and we're pulling out a subset, r items, and we're arranging them. So the order in which they get selected or they get placed makes the difference. Again, the key point when you're trying to decide between permutations and the next thing, which will be combinations, is does the order matter? Is it important? So for example, if we are arranging the 4 letters from the word math and seeing how many different words we can make, the order would matter. So this, and I'm using the term word loosely, it's just we're just using it as an arrangement of the 4 letters taking up these letters. So math is different than this. So those would be 2 different permutations or arrangements. What we're interested in is being able to count or find the total number of arrangements that can be made in different situations. So this is the notation we will use for permutations. So NPR is saying how many ways can you arrange R items that are pulled or taken from N items, or another way of saying that, as I said here, we're arranging N items taken R at a time. This is the terminology. This is the formula. See, it uses this factorial notation. So for example, if we had 20 runners competing in a, say, a cross-country race, and we're going to give 3 medals or ribbons, gold, silver, and bronze. So as you know, winning the race is different than coming in second or third. So this is a permutation problem, and we're looking at how many different finishes could there be. So this would be, the pool of numbers is 20, and we're arranging 3 at a time. We're arranging gold, silver, bronze. And if we plug into our formula, we would get this. Now we would have, this would be 20 on down to 1, and this would be 17 on down to 1. So every number from 17 all the way down to 1 all cancel out, so we're left with this. So this looks very familiar to that multiplication counting property that we used in the previous tutorial. Now let me bring a calculator up here and show how we could calculate that using the graphing calculator. Now to do that, we're going to enter the n number first, so I'm going to enter 20. And then we're going to press the math button here, and then go over to the probability matrix, not matrix, the probability menu, and NPR, our permutations, is item 2. Now we enter the R, which is 3, and press enter, and we get the same number here that we had when I did it by hand. So we just described how to use the calculator. So let's look at another example here. So let me bring the calculator back. We've got let me read the problem. We've got 15 people and we're forming committees, and the different committees would have different leadership positions, so the order does matter. So to do this one, it's going to be 15, and it's a permutation because we are assigning roles. So we need math button again, go to the probability menu, select item 2, and now we're selecting 3 people, 3-person committees. So let's put the 3 in there. So there would be 2,730 different committees that could be formed. Now, when we're using permutations, if some of the items in the pool that we're selecting from are duplicated, then we have to account for that, because in the arrangements using the first A and the fourth A from a permutations point of view, those are treated as different letters, but since they're the same, we have to remove or divide out the duplicate arrangements. So we get this formula here. It could be extended if there were 3 objects that were repeated. We would have another factorial thing on the bottom. So if we want to figure out how many arrangements for banana, we've got 1, 2, 3, 4, 5, 6 letters total, so that's our N. We've got an A that's repeated 3 times, so that would be R, 3 factorial, and we have 2 N's. So again, you can see here that we would do this calculation here, and there would be 60 different arrangements. If this had been a 6 letter word and none of the letters were repeated, this would be a 6, and then math, probability, NPR, and we would say, let's say we're using all 6 letters each time, we would have 720 possible arrangements. So because of the duplicated letters, there are fewer arrangements that we can make. Now let's switch gears to combinations, our groupings of items. In this case, the order that we select does not matter, and so it builds off of the permutations formula, but we have to remove our duplicates, so that's by dividing. Now most of the time in our class we're going to be using the graphing calculator to calculate this, so your main decision will be deciding, is it a combination or a permutation problem. So here's an example of a combination problem. We're picking 3 students, or it's like the committee problem, for an exemption. But in this case, whether you are picked first or third, you still get the same treatment. You still get the exemption. So this is a combination problem. It would be 29 C3. Using the formula I showed, this is the way we would calculate it. And again, using the calculator here, we would do 29. Math, probability. This time we're going to use combinations, number 3. And there are 3 people that we're selecting, or 3 in the group. So we have 3,654 different groupings that we could choose. Now, one of the reasons we want to be able to count things is because when we are doing probability, we need to know number of outcomes and total number of outcomes, success outcomes, etc. And sometimes it may be too many of them to list by hand to count, or it'll be error prone. So we can use combinations and permutations to accomplish that task. So in the example, we've got a club that has the set of members that I listed here. And in our first example, we're going to be picking a council. In this case, the first person chosen will be the president, second the VP, and third the treasurer. So since we have positions assigned, this is going to be a permutations problem. And we want to know the probability that this one person will be chosen as president. So we need to know, in terms of the success outcomes, it would be how many different committees could be formed, or councils that could be formed, where Ichabod was chosen first, and then two of these other people were chosen in the other order. And then we needed to divide that by the total number of councils that could be created. So if we look at that, the councils where Ichabod is president, the total number of councils, I messed up here. So again, the total number of councils where Ichabod is chosen first. So we're choosing Ichabod first, that's one. And then that means there are 10 people left to choose from for the second position, and now we've got 2 people in the committee and 8 here. So we're using that multiplication counting principle here to figure out our number of successful outcomes. So there are 72 councils that have Ichabod as president. And then we need to know the total number of councils, and that would be 10 people being chosen 3 at a time, and it's an arrangement, and we could do this in the calculator, and we get 1/10. So there's a 0.1 probability that Ichabod would be chosen president of this. Now let's look at our last example. In this case, we are using combinations. We want to know what's the probability that Ichabod will be chosen for the council. So we know that Ichabod will be chosen to be successful, and then we have groupings of 2 other people. So this would be 1 for Ichabod times the number of groupings of people not counting Ichabod. So that would be 9C2 because we're not counting Ichabod. And then the total number of councils would again be 10C3. Again, in this particular case, we don't care about leadership positions. And so we get 3 out of 10. So we've reviewed here today permutations, and remember the key thing there is order matters, such as finishing in a race, organizing and arranging books on a shelf, etc. And combinations where we're doing groupings, maybe selecting people to participate in a committee, or putting music into a playlist that's going to be maybe played, is going to be shuffled, so the order doesn't matter, it's just whether the song is in the playlist, things like that. So good luck using permutations and combinations.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you